So we talk about rock classification, and we have a physical a rock description. So the numbering is consistent with the reference. So you please do not think that if you are writing, for example, your what is it called, your project, that you can number like this. You cannot. The number of tables and figures are based on my reference, and because it would take me a lot of time to modify, so I left them. But I'm just saying this so that if you are writing your project or something, don't imagine that you can start numbering tables like this. You start from one, something logical, but this is just based on my reference, so that needs to be clear. So these are table 4748. While I was making the notes, it would take me some time to modify, so I just use the reference as indicated. Please record your attendance on the chat box. So the physical description um, are as shown in the tables we are going to see. The terminologies used to describe intact rock for strength and weathering are given in the tables shown. The importance of geology gains even more prominence in rock classification, since many rock formations seem to pose similar tunneling problems. It is important to describe and evaluate the stratigraphy of rock, since in a nutshell, when you because in fact in tunneling the our primary material is the rock, so we need to know how to describe, give it marks. In fact, it will it in part of this work is we are going to rate the rock from 0 to 40, 41 to 60, 61 to 80, and 81 to 100, just like we grade the students. And then this one will give you an idea of how good or how bad is the rock. Of course, from that grading, you find that very good rock is from 81 to 100, and maybe good fair rock, good rock 61 to 80, fair rock is 41 to 60, and poor rock is 0 to 40. Now, there are several ways of or several proposals of how to classify rock as we will see, but all are in a bid to try to give us, when you are an engineer or a designer, tunnel engineer, you need to have an idea of how good or how bad the rock is. Of course, we would really like to rocks if we have like so now you can see we have sedimentary rocks, the most problematic because these ones are more closer to soil. Of course, from your geology, that rocks have different modes of formation. We have sedimentary rock, igneous rock, and metamorphic rocks. So the soil, I mean the rocks that are a little bit the sedimentary rocks, because the age of formation is they are not as they have not formed for a long time, in comparison to other kinds of rock. So this table just show you the classification of sedimentary rocks. We talk about igneous rock and also metamorphic rock. Uh, all we are trying to do, or what we are looking for, is material of good strength. That's all we are interested in. So this is how to describe a rock in terms of the strength. So if we have very low a soft rock, then the This units are unfortunately in pounds per square inch. You can try to pound. I think you can, if you go online, you can convert and have an idea. So extremely soft rock is between 28 to 100. Very low strength is at 1,000 to 100 to 1,000, and the designation R1. So this the extremely soft rock can be indented by a thumbnail. Now, for a rock of very low strength, they crumble under firm blows with point geology peak. So, also can be peeled by a pocket knife. So this is for rocks of low strength, very low strength. So low strength is between 1,000 to 400. Uh, uh, PSI can be peeled by a pocket knife with difficulty. Shallow indentation made by firm blows of geology peak craters under uh, uh, point impact. Now, moderate strength are between 4,000 to 8,000. Cannot be scrapped or peeled by a pocket knife. Specimen can be fractured with single firm blow of geology hammer and will develop smooth pit or dent under point impact. Then medium high range are between 8,000 to 16,000. Specimen requires more than one blow with a geology hammer to fracture. It explosively dents or pits under geology hammer point impact. So we have high strength and just confirm. So let's take an average of 16. That's 20. That's 48. We take an average of 34. So just to see. So convert the. Let's see. Uh, convert convert PSI to MPa. Yeah. So if we have 24,000. So about 100. So actually 16,000 is between 110 and 32,000. So 100 between, so let's say between 100 and 200. That's 100 MPa and 200 MPa is we say is this is of very good okay, high strength, and then above 200 are 6. Sorry, this one is blocking. So that's a very good strength, we should say. And so the tunnels problems are governed by geology. I think we cannot stress this enough. And one might begin to predict the potential for some types of ground behavior just on the basis of geologic formation. So it's for starters, you need at least to know whether these are metamorphic or igneous rocks, because from the understanding, at least you can, from the conventional understanding, you can have an idea of the kind of behavior you expect. For instance, limestone formation frequently have solution joints or even karst features. So for example, when you have limestone have issues with acid water attack. They can form caves. So once you know this is limestone, you have an idea. Also, basalt formation have distinctive cooling joints and are susceptible to lava tubes. whenever the indicated geology is present. Such features may be expected and a potential effect on tunneling may be expected. In the above cases, this might be a potential for large water inflows. So differences between soil and rock behavior. Please, I know you have learned soil mechanics as well. We might use the same principles, but the behavior of rock and soil are totally different. So you need to be very careful. In fact, you need to be careful with soil, and in rock, you even need to be more careful because the behavior are different. Rock mass descriptions are even more complex than soils. Aside from the obvious greater strength of intact rock, the major difference in the behavior of rock from that of soils is that the dominant effect of anisotropy. So on the other discontinuities of the rock mass, these discontinuities range from texture or fabric in the rock, such as schisto's foliation, up to major faults in the rock mass. In the rock mass, attention to the details of jointing is extremely important for rock tunnels. Classification for joint spacing and for joint roughness are given in a table we will show later. So these are the things when you are going to give marks. You remember I told you we are gonna decide that this rock is we uh, we are going to decide, for example, that this rock has a rating of 41 or 50 something or 60 or 80. How we decide this is we check how intact the rock is. We check the strength, the unified, the uniaxial compressive strength. If it is between 0 to 2 MPa, that is very weak rock. And if it is between 2 and something, 2 and 8 or 2 and 10, 10 and 30 and something like this, over 50, 50 100, the same, actually in fact the same classification that I've shown you before. But so this is how you give it marks. So if you know the strength is between 0 and 2, then in terms of the marks that contributes to strength, you give it low marks. If there is presence of water, if there's a presence of a joint, how continuous or how discontinuous the joint is. So all these things will give it marks. Now the various joint sets play dominant role in kinematic behavior of rock masses because the rock, actually the joints have a great influence on the rock because the rock, if it is broken, the rock is as strong as its weakest point, and the weakest point obviously are the joints. So movement of rock blocks usually only takes place along joints, and thus movement can only be along the plane defining that joint. Further, the presence of joint drastically changes the rock mass's engineering properties. Joints determine the kinematic freedom of rock wedges have the kinematic freedom rock wedges have, and they dramatically affect the rock mass behavior, rock mass modulus. Further, they play a major role in the design and effectiveness of support of the underground opening, say by rock bolts. So a part of this course, you are going also to design rock bolts as well. So because you are anchoring bolts, let me show you here. If this is your tunnel, that's your tunnel. That's a very okay. Anyway, that's your tunnel, and there are there are breakages here somewhere. So the principle of bolt is rock bolt is you design something that can go past all the cracks, and then you anchor it with grout there. once you know that this is where the cracks are, you anchor it with grout there, and then you secure it firmly on the edge of the tunnel. So you can see the level, the extent of the crack determines the design of the rock bolt. Of course, the amount of force you apply, because you have to apply some force also on the rock bolt to make sure, because if they are loose, if these cracks make this place loose and maybe water can flow, and that's, you don't need that. So you need to make it stronger. So you have to apply some tensile force on the rock bolt to make sure if the cracks are loose, that well secured, and your tunnel is well protected. So all these affect the design of rock ball, like I've said. An undisturbed sample of soil taken from a core boring can often, but not always, be considered representative of the soil mass and strength test values, or any other engineering property. Values obtained on such samples are frequently attributed to soil mass. In rock, even more than in soil, a clear distinction must be made. So in soil, sometimes when you take a sample, you can reasonably agree that that is the representative sample, of course within certain limits. But for the soil, the for rock, the distinction a distinction has to be made between the intact rock and the engineering properties of rock mass, which include the effects of discontinuities. So you might take a sample, but the sample you have taken is only of an intact material. You have not taken a sample of probably a place where there are discontinuities. So you need to take care of all this, and the controlling behavior is the behavior of the rock mass, rather than the behavior of an isolated test that you have done from a limited sample. Such effects are important to rock tunnel projects. An intact rock from core boring suitable for testing most likely does not have the discontinuities that govern the behavior of the. So you have to look at the bigger picture, because when you sampling is important. We are not saying sampling is not important. When you sample, even when you interpret the data, you need to be aware it is possible there are discontinuities in the rock that your limited sample may not have captured. So for these reasons, you remember we talked about adits. When you're doing dams, adits, you do pits. So in addition to collecting the samples, you depending on the level, for example in the dam, you dig a pit uh, uh, to a depth of at least half of the dam, and if the conditions are worse, or in certain selected pits, you can do up to the same height of the dam, just so that you have a complete profile and you can pick these things that you might easily miss, like for example the discontinuity. At the end of the day, all you're looking for is to be able to completely describe the behavior of rock mass, rather than the behavior on intact rock. This same relationship of size of any tested zone to the scale of discontinuities must be understood during site characterization, to assure that the test results are not used incorrectly. For instance, a 3 feet diameter plate load test may give representative results if they are average spacing. If the average spacing, okay, this is the table we're talking about, but let's complete the thought. If the average spacing of discontinuity is just a few inches, but not if the average spacing of discontinuities is greater than 1 feet. So uh, for that sampling, if you have just a few inches of discontinuities, then probably the result of the test is closer to the rock mass behavior as in situ. However, if the spacing are large, then that is highly not representative. So this is in fact how to classify discontinuities. So if the discontinuities are less than 60 meters millimeters apart, then we say they are very close. Between 60 to 200, they are close and moderate. Again, this is part of the marks. You remember we had talked about the strength. Strength contributes to the marks. Now you can see presence of discontinuities or no discontinuity contributes to the marks. Again, now here, this is a third parameter, the joint spacing. So joint spacing, so the one with the highest marks is for the very close one has the highest marks. So each of these things have, I think, between 10, 15, some have 20, some have the maximum. But all of them will add up to 100. So when you have a rock mass, you check, is there any spacing? How spacing between discontinuities? How close are they? Are there discontinuities? And you grade accordingly. So depending on the maximum marks available, and then you are able to aggregate and say this rock scores 70 and therefore is a good rock, or scores 40 because it's a poor rock. Now again, another thing we need to or another parameter is fracture roughness. So this is the fourth thing. Uniaxial compressive strength. The And I suspect a good student would know what the teacher is stressing. So what's important? Uniaxial. So if you're asked to which parameters are used to classify rock, these are the highlights. We Uniaxial strength, whether there are discontinuities, that is one thing, and how close are the discontinuities apart from each other. The joint roughness, as you can see in the table, the so the jo- like I was explaining, if the joint spacing is not much, then the sample you take can be the coring the sample. If you take a diameter of 3 feet, then it might be representative of the behavior. However, if you have more discontinuities, then that sampling is not enough. Similarly, a 10 feet diameter tunnel may behave well in certain jointed rock, while a 30 feet diameter tunnel in the same rock may experience difficulties. A greater number of joints intersect larger opening with greater chance of a favorable joint orientations relative to a tunnel boundary and greater kinematic freedom. Rock characterization must address the inherent anisotropy of rock and the consequent strong directionality of any engineering properties. These are true not only in the small scale, where the fabric in the intact rock samples such as foliation make the rock anisotropic, but also in large scale, where the joints and the shear zones of faults make the rock mass uh, behave anisotropically or directionally. So the joints in the rock make rock masses behave like jigsaw, and a jigsaw puzzle, interlocking and the interaction of the rock blocks uh, uh, place certain constraints on the kinematics. So let me try to explain a little bit. If you have the rock mass probably like that, and then another one on top like this. So what we mean is this. So these edges will fit there, and this other fit there. So you can see it's like a jigsaw. That's what we are saying. And this will, and in fact, if this is acting as a rock mass, the behavior, this rock will be as strong as the joints. So this is why when you're giving it, characterizing it, you need to pay attention to the nature of the joints as well. Um, so kinematics of movement of any mass of rock in response to any external forces, including those caused by the excavation of a tunnel. Shear zones are persistent through going discontinuities, interrupt any interlocking effects, dramatically changing behavior of the rock, as shown in the figures. In the figure will show in situ stresses, both high and low, an important role in the behavior of jointed rock system. Many tunnels have experienced considerable difficulties, particularly at potholes or topographic lows, where stresses may be unusually low, as a stress of stress relaxation. As a result of stress relaxation during valley erosion, such cases result in open joints that carry water and are difficult to support in a tunnel heading. So the figures we were talking about. I think I need to show you the figures first. So figure 405 that we had explained. Sorry, this is the figure. So I don't know what are we saying about the figure. What did we say about the figure? The interlocking effects dramatically changing the behavior of the rock. Yes, in fact, at the you can see if so if this is uh, if this is, for example, the rock, the shear zone, you can see the interlocking behavior. Actually, will even make the rock look like it's intact, because of the friction between the the broken parts. So that interlock makes it look intact, but in fact the rock is as weak as its joints. So in order to provide a degree of no, I think there's something we have not talked about here. Finally, the permeability of rock mass is also dramatically related to discontinuities. Of course, you can imagine if you have a good rock, uh, the is or impervious more often than not, and then the water will tend to flow through the discontinuity. So the cracks propagate water, and of course will increase seepage. Of course, when water flows through the cracks, of course they will continue to increase the level of cracking. And so as the shear zone, so sometimes a discontinuity such as shear zone may be permeable and result in considerable water inflow. However, sometimes the shear zone may be impermeable and acts as a dam holding back abundant water on the other side at high heads that will be encountered suddenly upon tunneling through the zone. Even the concept of using an effective permeability coefficient is challenged in rock projects, because actually it's very difficult if you think about it. Because if you talk about something like soil is made of particles such that water can seep through in a fairly uniform way. Now rocks, you can find one intact piece of intact rock here, and mostly continuous and impermeable. Then you find a pocket of rocks with a lot of cracks and a lot of discontinuities, so water can flow through. So if, for example, you wanted to find permeability of rock, is difficult. Depends exactly on the position or the makeup or how broken the rock is. So even to describe the permeability of rock is a big problem. There's no universal agreement. Some people have come up with the idea of getting what we call effective permeability, and even then, there's no universal agreement whether this is a good representation of the permeability of the rock. The effective permeability of the rock mass is governed by discontinuities and other defects. By discontinuities and other defects. So in the rock rather than the permeability of the intact rock. Not only is this a permeability of rock mass anisotropic as it is in soil, but groundwater may pass easily through some joints or even some portions of the rock joint, but not through others. So you can see the challenges we are dealing with. In a nutshell, in broken rock, probably you find good high permeability if the rock is intact, and then the flow is only through the discontinuities, because if the rest of the rock is intact, the intact rock is likely impermeable or has very low impermeability, low permeability. I'm sorry, pardon me. Now now to the how can we classify rock. So, in order to provide a degree of organization and standardization to seemingly complex and confusing masses of field data, the concept of rock mass classification evolved. So, these classification systems give the geotechnical engineer or a geologist a method of assessing the relative importance of each rock parameter or geologic condition contained in the given classification system that is being used. So they are in a sense an extension of some same concept used in the soil mechanics in the unified classification and forerunner of what and are now called the expert systems. So the also like the UCS, the Unified Soil Classification System for the soil. I said that you can say this is well graded sand, poorly graded clay, silt or sand. We also in soil we have some way to help people to be able to so that engineers, basically geotechnical engineers, basically that they are able to uh, to classify soil, I mean rock. So these Barton uh, states that the Q system, so this one of the systems is essentially weighing process in which positive and negative aspects of rock are assessed. This is a good description of all rock masses classification systems uh, adopt. So in practice, uh, in practice, rock classification systems are generally used to predict behavior by applying the concept to data obtained by logging rock core and by logging rock outcrops. None of the system is perfect, and it may be necessary to adjust or fine tune the a particular rock classification system to fit the type of rock encountered and to account more properly for special behavior of the rock condition being characterized. Further, during the construction of the tunnel, the exposed rock can be logged to obtain input data which can be used to calibrate a rock mass classification system for use on future tunnels in the same geological environment. So the history of development of these methods. Tezagi in 1946 developed a method of classifying rock mass types that could be used to describe and evaluate rock load on steel supports. Although this classification is decades old, the rock mass terms and descriptions coined by Tezagi are still useful in communicating about the behavior of rock masses. The basic descriptions are given in table F of, for the table shown. In practice, there are no sharp boundaries between these rock categories, and the properties of the rocks indicated by each one of these terms can vary between wide limits. Loafers in 1958 developed a standard up time classification method that correlated stand up time of supported spans with rock mass equality. Many others throughout the world have contributed to the development of. So this is the a classification coined by Tezagi that intact rocks contains neither joints nor cracks, and this is stratified rocks and crushed rock and moderately jointed and swelling rock. So all these, in fact, if you will see in the methods that we are going to use for description, we our words or the adjectives do not go far from this. In fact, some of the adjectives are from this kind of description. So in the mid 1960s, someone, Dr. Don of the University of Illinois, developed an improved method logging called rock core to logging rock core to calculate modified core recovery a percentage called rock quality designation. So this is when you're doing core excavation, not pit. If you're doing a pit to see, you're collecting samples to take to the lab. Rock quality designation is by visual inspection, of course, measuring the length, how continuous or discontinuous. So if, for example, in length of 1 meter, you have recovered. First of all, if even a length of 1 meter, you have recovered a whole 1 meter which is intact, then in the terms of rock quality designation, that's 100%. Now, if you have two broken pieces, then that's 50%. So it has something to do with the length of the intact rock versus the length of the broken. So essentially, a simple measurement of percentage of good rock, good in quotes, in the core and intact four pieces. I think I've said that, or more than, or more. So pieces more than 4 inches in length or more, and has been found to have good, much better correlation to the actual behavior of rock than standard percent core recovery. It is it correctly reflects the fact that a rock mass that is so fractured or weathered can that there are no pieces of sound rock longer than 4 inches will also behave poorly during construction. It was the first time that the engineering behavior of rock mass could be estimated from I think RQD from subsequently subsequently rock mass classification systems were developed. Something is not rock classifications. Simple parameter. Okay. So something is not complete there then. Estimated from a simple parameter obtained from bore. So it was the first time that the engineering behavior rock mass could be estimated from simple parameter obtained from core logging. Yeah, so actually uh, this RQD is uh, it can be seen or can be observed from the as you do the borehole log, you can see in fact the nature of the rock. So subsequently, mass were developed mass classification systems that provided quantitative numerical. Of course, engineers will like numerical things that we can refer to. So it's because of this, we the methods that could give numerical values were developed. So this could take care of conditions such as the groundwater, joint spacing, I have said this before, orientation and condition, and intact rock strength. We have said uniaxial compressive strength in situ determined by certain tests, rock stress, etc., whose combined effect were previously described in more qualitative terms. So these researchers, Wickham, Tiedman, and Skinner in 1972 developed numerical systems that rates and weight rock mass parameters to correct rock mass quality and excavation dimension to ground support requirements. Skinner, that's 1998. RQD gained immediate acceptance and is now in common use worldwide. In fact, RQD is the basic parameter used in the two most widely used comprehensive rock classification system that have been developed in the last couple of decades. Actually, this is very common. The Let's see if I have something for you here. The In most of the geotechnical reports we write, which report do I have? They describe the. Do I know where these things are? Okay, there is some report here. These are these are private reports, and I'm recording this one, so I should stop recording.